So the next element I becomes plus plus, so I becomes 3. So now see, I 3 and n is 4. So again satisfying. So I'll move into this position. So now T becomes A of 3. What is in A of 3? 2. So the new element is 2. I have to insert 2. Okay. Now again, J will start from which value? I minus 1. I is now 3. So J will start from I minus 1 means it will start from 2. Okay. Now J is greater than equal to 0, satisfying. Now check this one. What is in temporary element? Temporary element is 2. And what is in A of 2? A of 2 is 5. So there is 5. Okay. So this one is satisfying, 5 greater than 2. So it will move into this part. Now A of 2, J is 2. So A of 2 is copied into A of 3. This is the position of A of 3. So A of 2 is copied into A of 3. So now 5 will come into this position. Clear? Now J minus minus, J becomes 1. Okay. Now J is satisfying this one. Now check this one. What is in A of 1? The A of 1, there is 4. So this is 4. This is temporary 2. 4 greater than 2. Again satisfying. So it will move into this part. A of 1 is copied into A of 2. A of 1 is 4, which is copied to A of 2. So 4 will come into this position. Okay. Then again J minus minus, J becomes 0. So J is satisfying this one, equal to 0. Now check this one. What is the element? Temporary is 2. What is the element? A of 0? A of 0 is 3. So again it is satisfying, 3 greater than 2. So it will move into this part. And what it will do? A of 0 will be copied into A of 1. A of 0 is 3, will be copied into A of 1. So 3 will come into this position. Okay. Now again J minus minus, minus 1. Not satisfying this one, coming out from this part. So now A of J plus 1 means J is minus 1, J plus 1 is 0. A of 0 means this position. So temporary is copied into this position. So 2 is copied into this position. So finally your array is 2, 3, 4, 5. See, after this, I plus plus, I becomes 4. Now this one is not satisfying. So it will come out from this value. So this is your sorted array. So this is your insertion sort and this is your sorted array. Okay. Now the next thing, the time complexity. So how to calculate the time complexity? For this, see, again the best case and worst case. Okay. Now best case means it is already sorted. In this particular sorting algorithm, the best case is if it is already sorted. If it is already sorted, see, if it is in reverse order of the sorted array, then it is the worst case. See, if it is already sorted, what you will do? You will compare 22 with only 11. No more comparison. So how many comparison? One comparison. For this, it will be compared with this. Since it is C, I have written it T less than A of J. So what is T? T is this one, 22, and A of J is this one. If A of J is greater than T, then only your loop will be run. Since it is not satisfying, so only one comparison. Only one comparison. Then for 33, again only one comparison. For 44, only one comparison. So if there are 4 elements, how many comparisons we have performed? 1 for 22, 1 for 33, 1 for 44. So only 3 comparison. It means for n number of elements, it is n minus 1 comparison. So your time complexity is order of n. Simple time complexity calculation. But if it is worst case, for this element 33, how many comparison? 1. Clear? Then it becomes 33, 44. Then for 22, how many comparison? First it will compare with 44, then it will compare with 33. So 2 comparisons. Then it becomes 22, 33, 44. For 11, first it will compare with 44, then 33, then 22. So 3 comparisons. So it is increasing by 1 value. So how many elements are there? There are 4 elements. For 4 elements, first you have compared with 1, then 2, then 3. So for n number of elements, it will be like this: 1 plus 2 plus dot 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 up to n minus 1. So it is same as bubble sort or selection sort. In bubble sort or selection sort, it is first n minus 1, then n minus 2, then n minus 3, and then it will gradually decrease. But here it will gradually increase. And the worst case time complexity again becomes order of n square. Best case time complexity is order of n. So see, this algorithm by default giving you best case and worst case different times. In simple bubble sort, we have seen the simple bubble sort cannot give you best case time complexity. That's why we have modified it. In selection sort, both best and worst, it will give you the same time complexity. But this insertion sort, for best case, it will give you best time complexity. For worst case, it will give you the worst time complexity. So the time complexity calculation is pretty simple. But there is one part. See, very interesting. Now see, we can improve this worst case time complexity. We can improve this. How we can improve this? We can improve this by applying some other algorithm into it. Why? See, whenever I am inserting a new element in this array, see, the array is already sorted. Na? When I am inserting new element, I am inserting the element in an array of sorted elements. So you can write it in insertion sort, new elements. So in insertion sort, new elements are inserted in an array of sorted elements. Is it true? Yes, it is true. So if I perform, see, since the array is already sorted, if I somehow perform binary search, what I am searching? I am searching what should be the position of this new element. Correct? When I am inserting a new element in the sorted array, in insertion sort, we are actually inserting or searching the position of this new element. And then I am inserting it in proper position. So if when I am applying, comparing with first this, then this, then this, so it is, I am applying sequential search. But if I apply binary search, what is the time complexity of sequential search? We already know the time complexity is order of n. Okay, so how many elements I have to insert in this way? I have to insert n elements. So the time complexity becomes order of n square. To insert one element, I require order of n time. To insert n elements, I require n into n, order of n square, simple logic. But if I perform binary search instead of sequential search, if I perform binary search, then we know the searching time complexity of binary search is order of log n. Correct? So if I take order of log n to insert one element, then to insert n elements, I should require order of n log n. Okay? So we can improve the time complexity of worst case by applying the binary search algorithm. So now in this lab, what you have to do, you have to implement. So this is your assignment 2. Assignment 2, implement insertion sort using binary search to improve the worst case time complexity. I hope the problem statement is clear, because I have already discussed what is insertion sort and how we can implement binary search. So so in this, what you have to implement, see, you have to write a binary search algorithm. You have to write a binary search algorithm from this binary, and what are the arguments that you have to pass in this binary search? You have to pass array, lowest index value, highest index value, and the element that you want to search. And it will return one position value, integer value. And what is that position? This integer, the return value is actually the position of the this newly inserted element. And then this value will be returned in the main insertion function. So this is main insertion sort function. In the main insertion function, it will call the binary search, say suppose position equal to bin search. It will call it like this. Then based on this position, it will apply a for loop to insert at this particular position. I have already done this, how to insert at particular position. So you have to, after getting this position, what you will do, you will insert the element into its proper position. So in this way, you have to implement the insertion sort. This is simple insertion sort. Sir, where we have implemented once more. Yeah, I'm explaining. This insertion sort is actually implemented on the basis of sequential search. We are comparing the newly inserted element with each and every element to select the proper position. But if I implement this with this binary search, what will happen? See, just a simple example. Suppose there is 11, 22, 33, 44, 55 already there. Now I have to insert a new element. Suppose the new element is, say, 15. I have to insert this. So this is already sorted. So I have to apply the binary search algorithm. So I will calculate the middle position. What is the middle position? Suppose this is the middle position. I will compare 15 with this. Okay, 15 is less than this. So I will go for searching into this position. Again, I will search the middle position. I will compare. Then I will. So finally, I will return from this binary search what should be the position of this 15. What should be the position of this 15? See, so this is lowest index value, highest index value. How, and the mid value is 0. So I will compare with this. Then 15 is greater than this. So in this way, your L and H will be modified. And finally, what you have to return? You have to return what should be the position. Suppose the return value from this binary search function is index value 1. It means I have to insert 15 into this position, in this particular position. So in insertion function, what I will do, I will first call this binary search. It will return me the position value. Position value is now 1. So I will insert the new element 15 into this position. What I will do, I will shift all the elements in this for loop. What I will do, I will perform the shifting of all these elements. I will shift all this element by one position. Then I will insert the new element into this proper position. So this is the thing that you have to implement. So this is your assignment 2. Is it clear now?